Grab the chair from the back. Six, seven, right there. 10, 11, 12, 14, 15, 16. Two, 4, 6, 8, 10, 12, 14, 16, 18. I'm missing one paper, I think. So if it's not turned in, it doesn't get graded. All right. All right, so looking at this real quick. I'm not going over the answers because I am grading it, but I am going to kind of show you what your intended setup would have been for each of these, just so that you can kind of be aware. All right, so this one I'm going from mole. I want to know how many moles, and I'm starting with atoms. So that means I'm going to need a conversion factor that uses Avogadro's number. So I would start off with my given 3.01 times 10 to the 23rd. 22 atoms. All right. And that's going to give me moles. And so that would give me my answer in mole of magnesium. All right. Going through on this one, how many atoms? And I'm starting in moles. All right, so 0.750 mole. I'm trying to get 2 atoms. So atoms is on top, mole is on bottom. 1 mole for every 6.022 times 10 to the 23rd. So that's going to give me atom of zinc. All right. This one, how many moles in grams? So on this one, I'm needing molar mass. So I'm starting out with 28 grams of carbon dioxide. I want to get rid of grams of carbon dioxide. So I need the molar mass right there, whatever the molar mass of carbon dioxide came out to. So 1 carbon, 2 oxygens, 12 plus 32. And so that's going to give me mole of CO2. All right. Now, coming down to number 4, it says, what is the mass of 5 moles of iron 3 oxide? So I'm trying to get to mass. I'm starting off with 5 mole. And the key thing is here is getting the correct formula. So that's saying iron 3. So iron 3 is Fe with a +3. Oxygen is a -2. So that means my formula is going to be Fe2O3. And then so you would need to get, so for every 1 mole of Fe2O3, I need to determine molar mass of Fe2O3. And so the last one is trying to get the mass in grams from molecules. So my first step is I need to go from molecules to moles. So I'm going to divide by Avogadro's number. To get to moles. And then once I'm in moles, then I'm going to multiply by the molar mass of F2. All right. And so that would have gotten us to the point on each one. So notice I didn't solve your molar masses or anything like that, didn't give you the answers, just wanted you to see where I'm going whenever I grade this. I will tell you on sheets like this is probably to your advantage to show as much work as possible. That way I can give partial credit. All right, moving on. So today we are going to be looking at empirical and molecular formulas. I'm going to be focusing on empirical formulas for the most part today. So on Monday, we started looking at molar mass. We also looked at percent composition. So an empirical formula is the formula we can get if we ever have the percent composition of something that we don't know what the subscripts are. And so this will allow us to get to the subscripts. So definition of an empirical formula is it consists of the symbols for the elements combined in a compound with the subscripts showing the smallest whole number ratio of different atoms in the compound. So if I had mainly you're going to see empirical formulas related to different covalent compounds. All right. So all 3 of these are compounds that contain carbon and hydrogen. And they are all different molecular compounds. So C6H6 is hexene. If it was in a ring structure, it'd be benzene. C4H4 is propene. And C8H8 is octene. All right. Now, these would all represent what we would call a molecular formula because it shows exactly what's there. All right. If I wanted to know the empirical formula for this, all 3 of those compounds have the same empirical formula. What would the empirical formula, the smallest whole number ratio, be for these? Be 1, because everything we can all, so all of them share the empirical formula of CH. And so this would be an empirical formula. Now, we can determine the empirical formula based off of percent composition. And we can find out what the subscript should be and all of that. Ionic compounds are always going to be written as an empirical formula. So I'll make that statement again. It'll probably be on the next slide, but because remember, whenever we use crisscross method and all of that, and we look at ionic compounds, the ionic compounds are always going to be written in the lowest form, or the simplest form. So they're always going to be reduced to that. Now, so again, the empirical formula contains the smallest possible whole numbers that can describe an atomic ratio, whereas the molecular formula, a definition for that, is the actual formula. It tells us exactly what's there. So empirical formulas do not tell us how many actual atoms are in the molecule. They also are not unique, meaning many molecular formulas or many molecules can have the same empirical formula. And we just saw that make sure it's registering again. Yay. Why my pen stopped working. There it is. All right, so we just saw where CH can be the empirical formula that matches all of these. C2H2, C4H4, C3H3. All of those can fit into there. Whereas I could have an empirical formula, CH2, like that, where CH2 could represent the same, those two empirical formulas of C2H4. All right, so this would be empirical. These would be molecular formulas that could be that. You can get bigger and bigger. Like there's more than that represents them. So if we look at acetylene has a molecular formula of C2H2. It's an empirical formula of CH. Benzene also has a molecular formula of C6H6, which is one of the ones I showed earlier. It's empirical formula of CH. But when we look at them molecularly, they're two completely different molecules. So again, our goal today is to kind of define how do we determine empirical formulas from experimentation. All right. So don't worry if you don't have the pictures or anything like that. I've shown them different ways. I just want you to understand that an empirical formula can represent more than one compound. All right, so here are the steps to obtaining an empirical formula. Molecular. All right, so we are only looking at empirical right now. So the first step is we need to obtain the mass of each element in the compound in grams. So if you're given percentages, remember that we can assume if I'm given percentages of elements, I can assume 100 grams. And so I can just convert those percentages to grams. All right. Because if I have percentages, they should all total up to 100. All right. The next step is we'll need to determine the moles of each type of atom present. So whenever we're talking about the moles, remember to get moles, if I have a mass, I can divide it by the molar mass off the periodic table, and then that'll give me a number of moles. The third step is we are going to establish a ratio of elements within there. So I'm going to divide the moles, each of the moles, by the element that has the smallest number of moles. When I do this in real time, when we do an example problem, this one will make more sense. We're just establishing a ratio to the smallest amount present. That way it puts the smallest amount present as 1. All right. All right. So step 4, we're going to convert convert those last numbers after the ratio. We'll divide them. We'll get a whole number that we'll use. So sometimes you're going to get a ratio here in a subscript that may end in like a 0.5, a 0.25, or a 0.33. That's not close enough to the whole number to round. And actually 0.33 or 0.66 and 0.25 or 0.75, we can't round those to whole numbers. So we have to multiply all of our subscripts by that. So if I get a number that's a 0.5, I'm going to multiply all of them by 2 to get whole numbers. All right. I'll multiply, if it's 0.25 or a 0.75, I'll multiply all of them by 4 because those are quarters, and it'll give me whole numbers. If I get something close to 0.3 or 0.6, then I'll multiply everything by 3 because those are all based off of thirds. And again, as we do this in practice, it'll make more sense. Now, the way that I do this, like I said, I struggled as a student keeping my data organized. So as I got older, I started putting things into charts. So the chart that I'm going to use is basically this setup. I have a column for the element, so I write down the chemical symbols of the elements involved. I have a column for mass, so I write down the masses involved. I have a column for moles that I write down the moles when I solve for them. And then I have a column for the ratio. Now, I don't always show the ratio. It just helps me remember to do it. And then I have a column for subscript that kind of gives me my final subscript. Once we get the subscripts, then we can put them in place and write our empirical formula. All right. So when we solve this, and this step 5 relates to what I have written in red, if you have any subscripts that come out to something 0.5 or something 0.25 or something 0.75 or something 0.33 or something 0.66, if it's 0.5, we're going to double it because 0.5 represents a half. And we double all the subscripts, not just the one that's 0.5. So if you do something to 1, you have to do it to all. And then same thing with the 0.25 or 75, you multiply by 4. If it's 0.33 or 66, you multiply by 3. There is one of the examples that I do will show this. So kind of pay attention when we do this. All right. anybody need more time on this one? I think that's the schedule. The schedule I printed out apparently was not the right schedule. All right. So if I had a problem that showed up on active, or if I had a problem that showed up on a homework sheet and it was stated like this, it says, what is the empirical formula of a compound that has 49.5% carbon, 5.2% hydrogen, 28.8% nitrogen, and 16.5% oxygen? So the first thing I would do is list out the elements that I have involved. So I have carbon, hydrogen, nitrogen, and oxygen available. Now, I need to figure out the masses of each of these. So notice the numbers are given to me in percentages. So I can assume that I have 100 grams of this sample. All right. So if I have 100 grams of this sample, I can use my percents as mass. So 49.5% becomes 49.5 grams. All right. Hydrogen, I have 5.2%. So I can assume that's 5.2 grams. Nitrogen, I have 28.8%, so that's 28.8 grams. And oxygen, 16.5 grams with 16.5%. Now, I need to convert this to moles. So what do I need to do to this mass to convert it to moles for carbon? To convert mass to moles, what do I do? Well, I'm already in grams, so I'm wanting to get rid of grams, right?
Molar mass.
So I'm putting molar mass on the bottom and mole on the top. So what would be the molar mass of carbon? 12.01. So 49.5 divided by 12.01. What number to 3 sig figs am I expecting there? So 49.5 divided by 12.01, I get 4.12. All right. What am I going to divide by for hydrogen? 1.01. So gives me around 5.1. I used 2 sig figs there because I only had 2 sig figs. All right. 28.8, nitrogen has an atomic mass of 14.01. So 28.8 divided by 14.01, I get 2.05. Now, my recommendation is make sure you know how I'm getting these numbers, that you're not just writing numbers down. Yes. Yes. That would round to 2.06. Thank you for catching that. All right. Because we get 2.055, so we can round that to 2.06. All right, and then 16.5, I'm going to divide by 16, and that's going to give me 1.03. Now, to establish my ratios, looking at step 3 or 4 now, to establish the ratio, I have to divide each of these by the smallest molar amount. So looking at this list, which one is my smallest molar amount? 1.03. So I'm going to divide 4.12 divided by 1.03. So these are my ratios. Everything is going to be divided by 1.03. So now when I get my subscripts, I'm just going to do this calculation. 4.12 divided by 1.03 gives me a number that should be fairly close to 4. Yeah, so I get exactly 4 on that one. 5.1 divided by 1.03. All right, so now on the next one, I get 4.95. 4.95 is close enough to 5 that I can round. All right. And then also for the next one, I get 1.99. 1.99 is close enough that I can round. And then 1.03 divided by 1.03 is 1. So based off of this, what should my chemical formula become? C4H5 N2O. All right. So this is a organic compound containing 4 carbons, 5 hydrogens, 2 nitrogens, and 1 oxygen. All right. So that is the basic setup. So I'm going to give us a very simple one for you to practice with and see. I just divide. So 4.12 divided by 1.03 gives me exactly 4. Going through on the rest of these, 5.1 divided by 1.03. Now notice I'm not caring about sig figs for a subscript because a subscript can only be in a whole number. All right. Yeah, always round. Now the catch is if I would have gotten a number like 1.5, I would have multiplied all of these by 2 because I want to get this to a whole number. 1.5 is not close enough that I can round either way. Yes. If it was 1.7, I'd multiply everything by 4 because 7 would be like 7.5, close to a quarter. 1.3, I'd multiply everything by 3 because that's a third. All right, so we're going to have an example of that on this next one. So does everybody have what they need off of this page? All right. All right, so what if you got this as your problem? Go ahead. I want you to try this one on your own. So it says, what is the empirical formula of a compound that's 31.0% boron and 69.0% oxygen? And I'll get you started. right, so you need to look up the molar mass of boron and divide 31. Take 31 divided by that molar mass, and that'll give you moles.
Like 5 seconds.
Yeah.
All right, now let's figure this out.
All right. So
How did you get
10.81. I looked at boron's molar mass. So
I'm sorry, I'm just very
31 divided by the molar mass of that element of B. 69 divided by the molar mass of that element, which is 16. To get to moles of boron, if you have a mass, to get to moles, you're going to divide by the molar mass. To get to moles of oxygen, I'm going to take whatever my mass of oxygen is, divide by 16. All right. Now, for ratio, what am I going to divide everything by at this point? 2.87. So 2.87 divided by 2.87. Like I said, this is the part that I don't usually show because it's just establishing. All right. So now, anything divided by itself is 1. What happens when we divide 4.31 by 2.87? 1.5. So 1.5 is, in this context, 1.5 is not close enough to 2 to round up to 2, and it's not close enough to 1 to round down to 1. So in this context, I can't have a half of a subscript. So I'm going to multiply this by 2, but because I'm multiplying this by 2, I also have to multiply this by 2. So 1 times 2 is 2. 1.5 times 2 gives me 3. So what is the empirical formula for this? B2O3. All right. Questions? All right. All right. Set a timer for 5 minutes. I want you to try this one on your own. So I'm not going to say anything until 5 minutes. Yes. All right. So let's look at this one real quick. All right. So doing this one, we're dealing with carbon, hydrogen, and oxygen, right? We have 40.1 grams of carbon. 6.6 grams of hydrogen, and 53.3 grams of oxygen. For the moles, I ended up, when I divide this by 12.01, I end up with 3.34. For this one, I ended up with 6.5. And for this one, for oxygen, I ended up with 3.33. Now, for my ratio, 3.34, 3.33, I don't really have to enter that in the calculator to know that that's going to be close enough to 1 to round. Yes. Yes. All right. 6.5 divided by 3.33. That gives me a number close enough to 2 that I can round. It gives me like 1.9, something like that. All right. And then 3.33 gives me 1. So what should my empirical formula be for this equation?
H2O.
All right. Now, go ahead and try to do number 3. So do number 3 off of this board. So we have a 170 gram sample of an unidentified compound containing 29.84 grams of sodium, 67.49 grams of chromium, and 72.67 grams of oxygen. Now, the thing that I'm going to ask before you start there, is there any piece of information that we don't really need? I don't need that to solve this equation. Yes. Favorite element? Don't really have one. I mean,
what's the most fun? I think boron sounds. It's boron. It sounds boring.
I like different ones for different reasons. I like strontium because it burns red. I like potassium because if you throw it in water, it's going to explode.
I like potassium. Have you ever done that before? It makes
I like chlorine because if you release it in a room, you can kill everybody. I mean,
What element do I use to have you watched Breaking Bad? What element would I use to start?
huh?
What element would I use?
It's not just an element; it's a compound.
What elements? What elements? Plural.
They don't leave much out in there.
So I can go through it all. Like, what did you use in order to do that?
I mean, let me phrase it like this. All right. So when I establish my ratios, 1.298 divided by 1.298 gives me 1. 1.298 divided by 1.298 gives me 1. 4.542 divided by 1.298 gives me 3.5. So in order to get it, I have to multiply everything by 2, and then that'll give us our formula.
Yes.
Na2Cr2O7. Yeah.
just